You've seen the word AI flash across your screen. You've heard titans like Jensen Huang of NVIDIA, Satya Nadella at Microsoft, and Sam Altman of OpenAI. You might even use GPT, or Google Gemini, or Grok from xAI. But do you truly grasp what this force is? Tonight we pull back the curtain and make it simple, with clear examples, bold truths, and a balance of wonder and warning. At the very heart of modern artificial intelligence lies a concept borrowed directly from the intricate architecture of the human brain. It's an elegant idea inspired by the billions of neurons that power our own thoughts and perceptions. This concept is called an artificial neural network. Think of it as a simplified digital blueprint of our brain's complex wiring. While it's far less complex than its biological counterpart, it operates on a similar principle of interconnected nodes processing information in concert. These digital neurons, or nodes, are organized into layers. Information enters at the input layer, travels through one or more hidden layers, and finally produces a result at the output layer. The journey is strictly one way, a forward cascade of calculations. But the real magic happens in the connections between these nodes. Each connection has a weight, a numerical value that acts like a volume knob, strengthening or weakening the signal passing through it. During training, the network learns by meticulously tuning these millions of knobs to produce the desired outcome. Let's see how it works. When you feed the network an image, it doesn't see a cat or a dog. It sees a grid of numbers representing the brightness and color of each pixel. This raw numerical data is the input. The first hidden layer might learn to recognize simple features, like edges or curves. The next layer takes these patterns and combines them into more complex shapes, like an eye or a pointed ear. Deeper still, another layer might assemble those shapes into a snout or a patch of fur. Each layer builds a more abstract, sophisticated understanding based on the work of the layer before it. Finally, the information reaches the output layer. After all the signals have been processed and weighted, the node with the strongest resulting signal wins, delivering the final verdict. CAT. When you hear the term deep learning, it simply refers to neural networks with many hidden layers, sometimes hundreds or even thousands. This depth is what gives them the power to recognize incredibly subtle and complex patterns in vast amounts of data. This fundamental architecture is remarkably versatile. While the core idea is the same, different tasks require different designs. Specialized networks known as transformers, for example, are the engines behind powerful language models like GPT, Claude, and Gemini, enabling them to understand and generate human-like text. But as these networks grow deeper and more complex, their appetite for computational power becomes immense. Training a frontier model requires massive-scale computing infrastructure, which is why specialized hardware like NVIDIA's H100 GPUs has become the essential fuel for pushing the boundaries of what AI can achieve. A new network starts clueless. Its knobs are random. To learn, it needs data, feedback, and repetition. Millions of examples with correct labels. This is supervised learning. If it guesses wrong, an error is measured. Backprop moves backward, tweaking the most guilty connections. Gradient descent is just finding which way is down toward better answers. It repeats, look, guess, check, adjust, again and again. Do this across billions of knobs, for weeks. Accuracy climbs. With enough data and compute, the model gets really good. That's machine learning in plain English. At their core, large language models like GPT or Gemini are sophisticated prediction engines. But they don't predict the future. They predict language itself. When you give them a prompt, they aren't thinking or understanding in a human sense. Instead, they are performing a complex statistical calculation to determine the most probable next word, or more accurately, the next token, a fragment of a word. The model considers the sequence of tokens it has already generated, and then chooses the most likely next one from a vast vocabulary of possibilities. It repeats this process, token by token, chaining together the most probable sequences to form coherent sentences, paragraphs, and even entire essays. This simple, iterative process, when performed at a massive scale, gives rise to surprisingly creative and fluent text. And scale is the crucial ingredient. The sheer size of these neural networks, with hundreds of billions or even trillions of parameters, allows them to absorb and encode the incredibly subtle patterns, nuances, and relationships within human language. This is the logic driving the intense competition in the field. Leaders like OpenAI, Anthropic, Google, and Microsoft are in a relentless race to build ever larger models, convinced that with greater scale comes greater capability. A similar principle applies to image generation, but the process is different. These models, often called diffusion models, learn from a massive dataset of images paired with descriptive text captions. They learn the association between the words "a cat sitting on a mat" and countless pictures of exactly that. During training, they practice a unique exercise. They systematically add random, chaotic noise to a clean image, step by step, until the original picture is completely obscured. Then, they learn the reverse process, how to meticulously remove that noise, guided by a text prompt, to reconstruct a coherent image. When you ask it to generate a new image, it starts with pure static and applies this learned denoising process, sculpting the chaos into a visual that matches your words. This fundamental need for scale is why new players, like Elon Musk's xAI, are also entering the fray, racing to acquire the vast amounts of data and computational power required to compete at the highest level. Ultimately, a model's power is a direct function of three key variables: the quality of its training data, the sheer quantity of that data, and the raw computational power, or compute, available to process it. The result is the emergence of bigger and bigger digital brains, tuned on the collective knowledge of the internet, capable of generating human-like text and photorealistic art on demand. The incredible power of generative AI to analyze and imitate artistic style has ignited a legal and ethical firestorm. For creators who have spent years honing a unique visual language, seeing machines echo their signature work with just a few keystrokes can feel deeply unsettling. It's not just one piece being copied, it's the very essence of their artistic identity being distilled into a replicable formula. At the heart of the conflict is a deceptively simple question. Is the AI learning from data, or is it simply copying it? This distinction is now being argued in courtrooms around the world. High-profile lawsuits like the one filed by the New York Times against OpenAI allege that their copyrighted articles were used without permission, not just for inspiration, but as the direct source material for training models that can now reproduce that content. Proponents argue the AI's process is analogous to a human studying and paraphrasing, a form of transformative use. But critics counter that the scale and precision of machine learning is fundamentally different, capable of memorizing and regenerating protected work in a way no human ever could. This anxiety extends far beyond the art world. Many professional jobs, from paralegals to programmers to financial analysts, are fundamentally based on recognizing and executing patterns. When an AI can perform these tasks in seconds, tasks that once defined a career, it's natural for people to feel exposed and vulnerable. The companies developing this technology insist their goal is to augment human capabilities, not replace them. They envision a future of co-pilots and assistants that handle the drudgery, freeing up humans for higher-level strategy and creativity. But the pain of that transition is real and already being felt. As a society, we are now forced to confront foundational questions. We must clearly define the boundaries of fair use, the nature of authorship, and the very definition of value in an age where creation can be automated. The legal and social precedents being set today will not just influence the next product cycle. They will shape the future of creativity, intellectual property, and countless livelihoods for generations to come. AI's superpower is pattern finding. AlphaFold cracked protein shapes. From sequences to 3D, accuracy leapt to breakthrough levels. That accelerates medicine and disease research worldwide. But encryption protects banking, messages, and states. Today, brute force takes ages, effectively impossible. Rumors like Q-star stoke fear. Progress in reasoning could change the game. AI need not find a formula. Approximation can be enough. It's a double-edged sword, cures or cracks in our defenses. We must plan for both outcomes, eyes wide open. As these digital brains grow, a question looms. Could an AI ever be conscious? Models speak like us, yet deny inner life. Critics say it's mimicry, no feelings, just patterns. But our minds are patterns in matter too. Neurons, synapses, signals. If complexity matches ours, where is the line exactly? Give it a body, senses, and years of learning. How would we know? We must build with curiosity and caution. Understand the basics. Join the debate. Help guide the rules.